Okay, I guess this is on. Thanks very much, Gary, and it's a pleasure to come down here. I actually have to go east to come to Los Angeles from Reno, but it's I like coming down here, and this is a great facility. And so the subject here is California's precipitation climate. I'll be talking about temperature too, because that does bear on precipitation. And this climate business is very complicated. A lot of different ways of talking about it. So I hope the way that I picked here is will carry some meaning, and you can ask a lot of questions if you still have some afterward if I miss something or don't go down the right pathway. So let's see if I can advance the thing. Okay. So just to start with, this is a map of annual precipitation in the western states, and just to show a couple of things. One is, it's organized basically according to topography, and there's more of it as you generally go from the reds down here to the blues and the purples up this way. But it's a very, very complicated picture spatially in the western states. But that is not to say that we can't understand almost every little piece of this diagram in the end. We put enough work on it. Homing in just a little bit, this is the northern part of California. Again, we have the heavy precipitation along the coast and in the Sierra. Anything on this map that's white is either less than 5 or greater than 100. Greater than 100 up here. Tulare Basin and parts of Death Valley and this area over here receives less than about 5 inches. And we zoom in on the southern part of the state, now it goes down to 2 inches. Still Death Valley is just a little bit less than 2 on up. In the western states, we go from 2 to about 280 or 290 just on the west slopes of Mount Olympus and the Olympic National Park. And if we zoom in a little bit more on this area, so where we have this large number of people here in this area right here, this scale is taken from something called PRISM, shows the mean annual precipitation, and you get quite a bit of precipitation up in the mountains. You're going from 0 to 12,000 feet in a very short distance, and there's lots of reasons why you get a lot of precipitation there. But it's not, these people do not live, all the people living here do not live on just the precipitation that falls in this one area, as I think you're pretty well aware. So how's this distributed in time? Well, it's a pretty simple picture. Even though we're not in the Mediterranean, it's called the Mediterranean climate because it has that same feature, which is it's wet in the winter and dry in the summer. These are long-term averages. Out on Anacapa Island, Topanga Ranger Station, and Cabrillo National Monument down in San Diego, it's just wet, dry, wet. It's pretty simple. And it's a pretty lengthy dry period in the summer where there is practically nothing to speak of that falls from the sky. So again, looking back at this picture here, we have in the western states, this is how precipitation is distributed. A lot up here, not so much down here. How are people distributed? Well, they left the light on for us. And so looking at the satellite photo of the lights, it's sort of proportional to the population. Of course, we have San Francisco and Sacramento up here, and then we have this large concentration of people, something like 18 or 20 million people down in this part of the state. So the people is where the water isn't. And so in order to get those together, California has developed this really strange river system. It's got rivers going all kinds of weird places. There's some rivers on here in blue that are actually following gravity from high to low. And there's other rivers on here that are actually following money, which can take them all kinds of directions. And then if you look at the city of Los Angeles and San Diego, all the way the whole metro area down here, there's basically 3 big straws that this area is drinking from. There's one straw that runs up here and drains this part of California, especially northern California. Then we got another straw that runs up the Owens Valley and drains the east side of the Sierra, and another straw that runs over to the Colorado River and drains all the way up into Wyoming and Utah and Colorado. And just took this off of Google Earth. But we have one of the stranger sites in the solar system, I think. when you look over here, I'm looking south up near Tracy, and you have the San Joaquin River over here on the left, draining from upper right to lower left. We have a couple of more rivers here, the Delta Mendota Canal and the California Aqueduct, running just the opposite direction and probably carrying more water than is actually coming down this way. And then we got a river of people going back and forth here on I-5, whatever they're up to. And we don't exactly see Huck Finn out here on the lazy rivers of California, these two big rivers that are right next to each other. And of course we've got this built canal system moving water this way and that way all around the state to relieve some of the inequalities in supply and demand. And finally we get down here to the Metropolitan Water District of Southern California. There's 26 different water districts that are part of this, from San Diego on up this way to near Ventura County, and the terminus of all these straws that I was just talking about that are pulling in water from this, that, and the other place, and a very complicated system here. I think it serves about 18 million people, if I have the number right, that are served by all these, and they're all different arrangements. There's some commonalities. There's a lot of differences too, and this is all built up over time, obviously. And this is just taking a look at it with some topography at it. It's mostly, most of the people are living out on a coastal plain here, the mountains, surrounded by the mountains. And so it's all at kind of low elevation, which does bear on a few of the things like desalinization and so forth, where you have to lift water. I mean, it's a lot easier to let gravity work for you than have to work against, because water is a heavy thing. So now flipping back into climate, we have something on our web pages at the Western Regional Climate Center called the California Climate Tracker. And I hardly ever give out URLs anymore. The only thing you have to remember in life is the word Google. And then you can dredge up just about every other thing that you forgot. And so if you Google this, you'll come across this page, and you click on this here. You can go into the little menu system. And we did a very extensive analysis of the state of California to try to divide it up into some regions that made sense climatically, of regions that kind of work with each other and go together in the way the climate functions. So first of all, looking at this region I call H down here, it's a little narrow band along the coast. It doesn't go very far inland because you start to get higher in altitude, which is another division here. So focusing on this one called H, that's this division. So what I've plotted here is the average of precipitation on a 4-kilometer basis, all added up on a grid basis, from 1895-96 through 2010 and 11 for what's called the water year, which is the period from October through September. It's in wide usage around the United States, and that just ended a couple weeks ago. So this is up through last year, and so this is the annual precipitation from 1895-96 up through this year. And you can see the year we just finished right there, which is respectable. It's not among the highest, but it's not among the lowest. And we were expecting less, which I'll show you in a little bit. But there's a couple of things to point out on this graph. One is precipitation really fluctuates a lot in this area. It fluctuates more here than any other part of the United States, to tell you the truth, in its relative fluctuation. I'll show you something on that in a little bit. But we have the driest and the wettest just within a few years of each other here. Another thing is the orange line here is a 11-year running mean, just to smooth it out a little bit. We don't see a lot of trend over this whole last 70 or 80 years or so. Been a lot up and down, but to the degree we can discern, there isn't much of a trend here. So this is South Coastal California. So what about, excuse me, what about temperature? The reason why temperature, we keep bringing up temperature when we talk about water, is temperature has an influence on how effective water can be made to do what we want it to do. In general, we like water that is cooler rather than warmer because it sinks into the soil better. When it falls as snow, it's generally better than if it falls as rain. And when you get precipitation that's warmer, it doesn't a lot more of it evaporates and doesn't participate in the hydrological cycle. And it also influences the demand for water. So this is the water year temperature for the South Coast area. And again, it goes back to 1895. And so we have the first part of last century up through about 1975 or so was kind of on the cool side. This average is from 1949 to 2005 that's plotted here. And starting around the 80s, we started to see a lot of warm years. They've kind of leveled out, and in fact, last year, and you can barely see it there, is the most recent year right there, is practically equal to the long-term mean. It cooled off in the last couple of years. So this is the South Coast. So let's look at the difference between day and night. Daytime is on the left, nighttime is on the right. They actually behave differently. Nighttime is a little bit more ambiguous. It has been coming up, but, daytime. And the daytime temperatures in this part of the state, averaged over 12 months, have been kind of low the last 2 years. Nighttime temperatures have been consistently warm over about the last 30 years, and the last year or two has still been kind of warm. So the difference between day and night is sort of like the difference between day and night in terms of temperature. When we look at so this is just summer, because people pay a lot of attention to that around here. And it's pretty well known because of the fog and so forth. So here's June, July, August temperature. And you can see the last 2 summers, the summer before last received a lot of comment because it was one of the cooler ones going back to the 50s. But last summer was almost as cool as this summer. And this is the part of California where when winter gets here, you can put away your winter clothes because summer's over. For the maximum temperature in the same area, actually the maximums were much cooler than average, and last year, this current year, they were again cooler, and the minimums were, last year, minimums, even the minimums were cool, and this year they're right near average. And over here. Okay, so we can think of, so we start out with precipitation, and Jeanine will get on to some of these issues of how, of this translation of what the sky brings, which is then run through this complicated hydrologic system, which has got all kinds of features to it, and it turns out, you run the crank, and out comes, on the other end, either stream flow or maybe groundwater, something like that. But it's not a straightforward translation from one to the other. And just to illustrate this is again that South Coast precipitation, and you see something like this. I think it's the Santa Clarita River, Piru Reservoir up here, and you see down in Southern California, you see little streams like this with great big stream beds, and you think, well, it seems like it has pretty high aspirations, I guess, to fill that up. But it does happen, as you well know. I think, well, maybe it's a little bit big for its britches, but this has to do with the variability of the region that this is an expression of. So let's look at the whole state. This is adding up something like 32,000 little pixels around the state of California. And again, we just finished a pretty decent water year. It's among the higher ones, but not the highest. There isn't much trend averaged over the state in its precipitation. This is something we update this, by the way, every month, on the 1st or 2nd of every month. And you can go in and look at this yourself on the web. You can run all these graphs off. If we go over here to this region, Sierra Nevada, which is where a lot of the important part of the precipitation for the state comes from, it was relatively higher. It's one of the higher ones. It's still not the highest. The highest ones are in the early 80s. Those 2 big El Nino years really do stand out. They stand out all over the West, actually. But it's a relatively decent year, and again, the state as a whole has not had much change in its precipitation over the long haul. A couple pictures here from Tom Knudsen sent me from the Sacramento Bee. Here's the store at Soda Springs. There's the door right there. That's about the size of a human being, and there's the top of the snowpack right up here. And this is a picture somebody took off of their 3rd floor balcony at Serene Lake. You can see you need a ladder to get up to the top of the snow, and he's up there shoveling out the power lines to this condominium. It's kind of dangerous to be walking around and tripping over power lines, which they normally don't. Only if you're in the NBA do you run into that. So, and this is a statewide temperature, and this is the history of California's temperature. I'm kind of going at this backwards. I often start out with the climate change stuff first and then go into the observation. I'm starting with the observations now. And there's been a general warming of the state, and a lot of this has taken place in the last few years here. And again, if we divide this into max and min, this is something we see quite a bit around the West. There really hasn't been a lot of change, averaged over the state again, in the maximum temperatures. There's been a little bit of rise here lately. We've had 2 cool years in a row now. But the minimums really have a lot more going on, it seems like. There's been a whole spate of pretty warm night times. And they started around the late 70s, early 80s or so. So I'm just flipping gears here now. So we're talking about precipitation. Another issue that comes up quite a bit is groundwater. We were trying to, I raised this question here in terms of drought monitoring and so forth, but in terms of one of the water supplies, obviously we poke holes in the ground and pull water out. And there's a lot of water, even in the Great Basin in Nevada. I was over in eastern Nevada just a few days ago looking at the situation over there, where Las Vegas has some designs on pulling water out here and shipping it south, all of the Owens Valley, which comes up all the time. And there's a lot of groundwater pumpage in this area down around here, especially. It is a component of the water balance here. How do we measure this? Well, we can put in monitoring wells, which has been done in parts of the Central Valley. And I just want to point out one other interesting way of doing it. There's a satellite up there called GRACE. It stands for something like Gravity Recovery Experiment. I can't remember all the words. But it's got 2 satellites that are about 200 miles apart, and they're going around the Earth like this. They keep the same distance between them. And when one of them goes over a little bit more mass, it speeds up before the other one speeds up, so it gets further apart. And these 2 satellites are constantly comparing how far apart they are from each other. And they can measure that to within about 1 human hair over a couple hundred miles. It's a very fine measurement. And then it gets past that little mass concentration, it slows down a little bit, the other satellite speeds up so they get closer together, and it measures this distance between them. And the thing that affects this is the amount of mass there. Well, the amount of mass could be the amount of water that's in like the Greenland ice cap, or in this case it happens to be the amount of water that's underground in the Central Valley. So when they're pumping water out, they're taking water out of the ground, and actually they've been able to measure, just through gravity, just the amount of water. So you can't hide gravity from a satellite, even though groundwater is hidden from us. You can't hide the effects of gravity. And this is turning out to be a really interesting way of measuring water all around the world in places where we don't have any other ground measurements. And even in places like California, where it's hard to measure, you have to subtract out a lot of effects. But it's a really interesting kind of idea, and it's kind of caught on, and now they want to put up another mission that will extend this current one when it runs out. So, as I was pointing out a little bit earlier, one of the straws that comes out of Southern California runs over here to the Colorado River near Davis Dam, and the Colorado drains this area up here, and especially most of the water, about 85% of the water in the Colorado River system comes from about 15% of its area. And that 15% is all these high mountains here. This high mountain water, there's hardly anything added along the way. In fact, it's even subtracted a little bit in some places. So we have another tool on our webpage. We can go in and click on a bunch of hydrologic basins, and you can pull up these yourself and get a history of the precipitation for the upper Colorado River Basin, because this is this point right here is where the Colorado River Compact divides the Colorado in the upper and the lower Colorado. So we're just looking at the upper Colorado, where the water comes from, and the water year they just finished a few weeks ago was one of the wetter ones in some time. They've had some real drought years, which is why the reservoirs have come down. Had a big year in 2005 and had another big year in 2011. Some kind of neither nor years here. The wettest period is generally in the 80s and sometimes the 90s. You see this quite commonly around the West, and especially in the Southwest. This period here being one of the wetter periods in the last 100 years or so. Meanwhile, the temperature has been kind of steadily rising, and it was rising quite a bit in the Colorado River Basin. Now it's been fluctuating a lot. 2 of the last 3 years have been on the cool side. Again, max and min. The maxes have dropped a fair amount. The mins have stayed kind of high. Even they've come down a little bit, but they're still above the long-term mean for the temperature. So this is the history of the water level of Lake Powell, which is just upstream from the Lee's Ferry measurement point on the Colorado River. And it shows, since it started to fill in 1963, it's full at about this level right here, 24.17. Excuse me. And this year, it came up quite a bit, and it's come down since. Right now, it's either 72% full or 28% empty, depending on your philosophical inclination and so forth. And the water level, when it's full, it's at 3,700 feet. This year, it came up 50 feet, and it's dropped back down about 10 feet. And this is the reservoir downstream of there, Lake Mead. Lake Mead and Powell are kind of operated as in tandem, as a pair. They're the 2 biggest reservoirs by far in the United States, and the Colorado, as a consequence, has about 4 years' worth of supply in those 2 reservoirs and a few other reservoirs on the system. It could keep the Colorado River going without any new precipitation for about 4 years while these dams were empty. So Lake Mead has a nice bathtub ring around it. I just flew over it again coming in here today, and it's come up a little bit, but not much. Starting about 1999, we started out a thing nationally called the U.S. Drought Monitor, and I've shown what this map looks like at the end of the water year, around the end of September, every year since 1999, just to give you a flavor of how it's varied. And the point I want to bring out here is that during this entire time, every year in the western states, there's been some element of drought. Some part of the West has been in drought. Drought is no stranger here. Comes and goes, it moves around. Takes vacations and goes somewhere else, but it always comes back, it seems. And bringing it up to date, this is what it looks like right now. There is not that much drought in the western states, except here in Arizona and New Mexico, which are participants in this southern drought in Texas, which is really the home of drought at the moment. So how do we get at some of the further history? Well, it turns out we have these kind of a couple of oaks. There's blue oak and valley oak that live in California. They live about 200 to 500 years or so. It turns out these are highly correlated. Their ring width is highly correlated with precipitation. It's one of the best correlated tree species on Earth, and correlations of 0.8 and 0.9. Of ring width with annual precipitation. They seem to be very good indicators. And they grow in kind of a bathtub ring around the Central Valley, and from anywhere from about 100 to 1,200 meters, or maybe 300 to 3,500 feet, or around 4,000 feet or so. And there's been an active coring program for those. And I'm just showing what the history of California precipitation since about 1600 has been up to around the year 2000. We don't have really, really long droughts in here, but we have some that are on the order of 10 or 15 years or so that we can see occasionally. And this is every year in the record. And we can pick out particularly big years. I was looking for 1861, 62, which would be right through here. It's just kind of a modest year in tree rings. Maybe it's that one there. It's not as big as the one later in 1869 or 70. But it is a pretty faithful recorder of drought in California. We can get even longer records from the Colorado River, also from tree rings. One nice thing about these dry areas is evidence doesn't decay. And so we have a record here going back to the year 800 of the flow on the Colorado River based on tree rings, and we can correlate it very well with what it's been over the last 100 years or so to calibrate this record. And a couple of things, when they signed the Colorado River Compact, that was right during this period right here. They divided up water. They thought, this is how much water is in the Colorado. And this is what we live with today. This is the legacy. This was signed in 1922. But later on, we found out, well, gee, the Colorado River has a lot of droughts that last, this is a 20-year running mean, a lot of droughts that last 10 or 20 years, and we have some that even last 40 or 50 years. That happen naturally. And we didn't know this back then, and we just found this out just a few years ago, really. So this is something we have to factor into account when I get into the climate change issue I'll bring up here in a little bit. Is the drought that we've just gone through, is it one of these kinds of drought or is it some new kind of drought? So another thing that affects us here is the world's oceans. And this is a map of the parts of the Earth that are about 26 or 27 degrees C or more in red. And we can plot for this area right through here what the temperatures have been doing of the ocean. I have them back to about 1950 here, and we had a long period up to 1976 where we had a lot of La Niñas when it was cool in that one region. And then we got into a regime where we had a lot of El Niños and hardly any La Niñas. People forgot what La Niña even was, practically, because people studying this issue didn't even hardly see them during their career. Then we had a big El Nino in 97, 98, and we've kind of gone back and forth, and we've had more La Niñas lately, and we had the strongest one last year that we've had in about the last 50 years or so. And it's not as strong this year, but we're seeing a resurgence of La Niña. And this is what the sea surface temperatures looked like last week. Blue means cool, warmer than usual. In these places here, it's warmer than usual up here because we had a huge melt of the ice pack, and it's the second lowest on record in the Arctic this year, and it hasn't all frozen back yet. So that's what La Niña looks like, and this is just homing in on the Pacific, and the history for the last 12 months or so. This Nino 3.4 region right here shows a year ago up through, it got almost near average, and it's come back down again. So we're back into a La Niña condition. And what La Niña means for the western states, it only has really an effect in winter. La Niña generally means dry in the red areas here, and it means wet in the purple and blue and green areas up here. This is based on about 60 or 70 years worth of data. Statistically speaking, if you look at the whole state of Arizona, we have La Niña conditions, which are in blue on the right here. All of them are drier than usual. La Niña practically guarantees you're going to have a dry winter in Arizona. El Nino allows it to get really, really wet, and it's hard to get wet in Arizona without El Nino, have a really wet winter. You practically need one to be in the top bunch. But it doesn't guarantee it because there's some El Nino winters that are dry there. So it's unreliably wet here and reliably dry here. And the same is true for Southern California. The same type of diagram. All the years that we measured were below normal with La Niña and all over the map, but generally higher, about double, with El Nino than La Niña, until last year. So this is sort of the exception that proves the rule, I guess. So our index was at 1.53, and the amount was about 24.7, so it was about up here. It's the first blue data point up in this part of the diagram in the last 80 years or so. We don't know why. Okay? We're having another La Niña. I think the odds would still favor, probably it's going to be dry. We don't know why last year worked out the way it did. And that started in October. It was already underway by now, last year. So this is how the year ended up, the water year that we just finished. Blue and purple are positive. So we had a swath that ran kind of southwest to northeast. Normally La Niña brings wet conditions up here, but they came further south than usual. It turned out that most of Arizona and all of New Mexico did have a very, very dry winter, and that did go into the monsoon season as well, although there's not a very good association of La Niña and El Nino with the monsoon season. There's also quite a strong relationship. On the left-hand side, it's precipitation. On the right-hand side, it's stream flow. If we looked at really heavy precipitation and really high stream flow, the stream flow really seems to get accentuated by El Nino and La Niña. What this says, this red here, means that when we have El Nino, we get higher than normal stream flows. When we have La Niña, we get higher than normal stream flows up this way. There's an out-of-phase relationship between the northern western U.S. and the southern part of the western U.S. Very strongly out of phase. And that's even accentuated in the stream flow records. The stream flow seems to magnify the temperature signal. A few years ago, as part of a National Research Council study of the American River, which when they built the reservoir, it was sized on this record right here, up to right here. This is how big does the reservoir have to be? Well, let's look at the observed record. Okay, well that tells us. Almost the day they put it into operation, they got that peak right there, and they're sitting there looking at each other like, the water, we're gonna have to run water over the spillways on the day we open this thing. Did we size this right? Then they got another one, and they got another one, and then they got a bigger one, and they got a bigger one, and this is the city of Sacramento that this protects, which a lot of people call America's Katrina. It's the next big disaster waiting to happen, because it doesn't take much more of one of these. It would have taken just one more hour of the precipitation that was part of this to go over the tops of the levees there. And they're wondering if the city of Sacramento is protected well enough. They've taken some steps since this study, but we don't, why is it going up like this? That was the central question. And again, we really don't know. Is this a climate change thing or something else? And another interesting thing with La Nina, as part of this study, I pulled out a bunch of the flood records, and it turns out in the Sierra Nevada, the floods, the biggest floods on record, these are the El Nino floods. You take all the big floods in the Sierra, you have to come down to about number 10 before you find one in an El Nino year. But 4 of the 5 top biggest ones are in La Nina years. So they seem to, the situation, the setting seems to be able to occur more frequently in a La Nina year, that if things line up right, and the Sierra seem to be able to get bigger floods in La Nina years, so the flood risk seems to go up a little bit in those years. And there's some reasons I think that are behind that I don't want to go into right at the moment, but I think they have to do with mountain orographic enhancement. So because of this, there's a new movie that just came out. It's a ski movie, actually. My brother sent this to me from Montana a couple days ago, Attack of La Nina. So we'll see what it brings to California this year. Excuse me. So this is for the United States, the same map I just showed of the western states, but it's for the whole country. So not only were we wet, but they had that huge amount of precipitation up here that, it flooded Minot, and Devil's Lake is an ongoing problem. All the stuff from Irene, and then the Texas drought here, and the southeast drought, which are just the opposite. The water year ended quite warm here, but actually rather cool in the western states. And this is just the summer. Again, a very hot summer here. The 2 hottest summers on record ever for any state in the United States were in Oklahoma and Texas this year. But we kind of lucked out, and we kind of ended up about near average. So I wanted to go into another issue here of extremes. I think I better move this along a little bit. Because it's really important for design and so forth. When an engineer is building something, they want to know how much precipitation is going to fall in what amount of time. And one of the issues with climate change is how much of that, how much is that going to change? These curves are what they have the likelihood across the bottom once every other year to once every 1,000 years, and then the duration is the different colors from 5 minutes up to 60 days. And then here's the amount. And if you're building a roof, or if you're building a culvert, or if you're building a detention pond, or a tailings pond for a mine, or any kind of thing people build, they look at these curves. They're obligated to follow these curves. And there's a couple of ways of presenting them. The other way is in terms of the intensity, which is the rate per time. In other words, the amount per time, which is a rate. You can present it either way. People who build microwave towers are interested in this, like civil defense purposes. So I wanted to get into these things called atmospheric rivers. And this is a map of the number of 3-day episodes over the last 60 years where some spot in the United States has had 16 inches of precipitation in 3 days. So these locations here, well, obviously they're probably hurricanes, and the color is proportional to the number. So they've had 1, a couple of them had 2. The only other place you see these in the United States, basically, is in California. And you see places that have had multiple instances. So this turns out to be really interesting. The 2 most extreme places are either the Gulf states or California. And if you look at different categories, this is 2 to 300, so that's 8 to 12 inches, 12 to 16, 16 to 20 inches, and greater than 20 inches in red, 20 inches in 3 days. California can equal any other part of the United States. And in fact, it has some fantastic, it's able to gin up very heavy amounts of precipitation in a hurry. And a really interesting statistic is when we had the 93 floods on the Mississippi, it took about 30 days to generate those big floods. During the 97-98 flood up here, it took about 3 days to generate 60% of that same amount. California can really generate very heavy precipitation. This inset over here shows that most of those in the eastern U.S. occur in the summer months, and they occur almost exclusively in the winter months in California, as you would be well aware. This is just a map showing the sort of the variability of precipitation. It's called the coefficient of variation, standard deviation divided by the mean. And what it shows for temperature, for precip and for stream flow, is that this varies here more than almost any other part of the United States. It's highly variable, especially down here along the south coast. Los Angeles, gets half of its precipitation falls in about 10 days. They only get 35 days at the airport with 1/100 of an inch, and 8 days with a ½ inch, and 3 days with an inch. It gets about 12 or 13 inches. So about 10 days are responsible for about half the precipitation. It's whether you get those 10 days or not that usually makes a winter. So they've discovered these things called atmospheric rivers, and you can see an example of one here. They're plumes of moisture that can stretch across the Pacific. They're very narrow, and they have a huge amount of moisture in them. They're kind of like a fire hose aimed at a spot. And when they aim at you for a few days, you get a lot of precipitation, and next door doesn't get all that much. So if they flop around like a fire hose might, they'll bring a lot of precipitation to a band. But if they sort of stay put, which they do once in a while, they seem to be responsible for responsible for floods in California along the west coast. I think I'm going to skip this one. I don't want to go into it too much. But they've just found these out in the last 5 or 10 years. A lot of floods involve these, and in fact, all the big floods in California have involved atmospheric rivers, and it's kind of hard not to have one of these rivers form and not get a flood someplace from it. And they also they've also inspired this new thing called arc storm. It's inspired by the 1861-62 floods, which were some of the biggest floods in California's history, and its recorded history anyway, where the entire inland part of California, about 300 miles long and about 60 miles wide, was flooded. About 25% of the assessed value of California was underwater at the time. Really phenomenal floods. I haven't seen anything like it. But it turns out, you look at some of the paleo records, there seems to be about 6 of these events that have occurred in the last couple thousand years. Really phenomenal events. There might have been one in 1805. There's a lot of evidence of something that happened in 1605, where sediment is found out in Santa Barbara Channel. And so this has been a scenario for a major planning effort for the state called arc storm, which I'll mention in a second. So anyway, these atmospheric rivers contribute a pretty sizable amount down here, 30 to 40 to 50% of the total precipitation, these heavy precipitation events. I'll skip this one. And here's an example from November of 2006 that happened to go up in the Pacific Northwest. And these 3 spots here in Oregon and Washington and Idaho all set all-time state records for 24-hour precipitation from the same storm. And this little square here is up at Mini Glacier Lodge, which some of you might have been to in Glacier National Park. Its ground floor was flooded. You probably wouldn't want to drive across the channel here. But this is on the east side of the divide. So this is out in heading out into the plains. And so this arc storm scenario is something that was concocted as a planning exercise for the state. When Governor Stanford had to go to his inauguration, he had to row actually to that, and they moved the state capital for a while in Sacramento in '62. They've strung together some plausible storms from 1968 and tacked on 2 big storms from 1969, January of '69, which really flooded this part of California. They tossed in 1 extra day for good measure, and then they waited a couple weeks and stuck on a storm in Northern California that was from 1986, the big flood then. And the idea here is to sort of test the whole state's response system to a major flood. This is a very plausible thing that could happen here in California. based on something called the Great California Shakeout, which is what if the LA basin got a magnitude 8 quake. And they kind of tested out all the facilities. They really learned a lot from it. And they've been learning a lot from this exercise, just as a planning exercise. Well, if this happened, we couldn't communicate with those folks, and we never even thought about that, and a whole bunch of things like that that have come out of this. It's called ArcStorm. It's a very interesting exercise. So I don't think I want to go through all these, just pointing out some of the connections in the state. Just want to talk a little bit about climate change. What is driving climate change? So on the this is a graph of the forcings that control global climate from 1880 up through just recently. This is greenhouse gases up here, which are causing the climate to get warm up. These are the aerosols, little particles in the air that are actually cooling the Earth's climate. And there's a kind of a competition between those going on. These are volcanoes, which cool off the Earth a little bit for short intervals of 2 or 3 years. Sunspots is this little wiggle right here. Sunspots have almost no effect on climate in terms of the energy. It's about 0.1% that they vary the energy input. So the effect of these is calling for, this is about 20 years from now, more precipitation up here, less precipitation down here, a kind of dividing line that runs through here. This is based on something like 19 different climate models. And this is part of a pattern that's seen around the Earth of basically the desert zones expanding northward, the tropical wet zones that are already wet getting wetter, and in both hemispheres, and then the higher latitudes getting wetter. So wet, dry, wet. The wet getting wetter, the dry getting drier, to a sort of a first approximation. And this is how the IPCC put it, the Intergovernmental Panel on Climate Change. Annual, winter, summer. The temperature across the top, a little bit more in summer than winter, but kind of comparable. For precipitation, in the winter months, wetter in the north, drier in the south. For the summer months, wetter in the north, drier in the south, but the dryness extending all the way on up to the United States. So basically what this does is it takes that winter season, it makes it a little bit shorter, but more intense, and it spreads out the spring and the summer and a little bit the fall. It concentrates more of the precipitation in the winter and reduces it in the summer. And this has a consequence for the way we manage water all by itself, even if we don't get much change in the total amount. And the bottom is a map of how much these agree with each other. If it's a deep green, they agree a lot on wet. If it's a deep brown, they agree a lot on dry. If it's kind of in between, the models are sort of different opinions, basically. So what have we seen? This is an area near Susanville, and if you run these back to 1900, we should have started to see some warming occur about the middle 70s or so, and by now it should be up about 1 degree or so. There's a whole variety of models and a whole variety of emission scenarios. Same thing for precipitation. Here's 0 right here, 0 change, and probably not a lot of precipitation change. That would be very easy to distinguish. So what have we seen in the western states over this area? This is what the temperature has done. It's been rising since about the 70s. It's fallen off in the last 2 or 3 years, but before that there's a steady rise and a little bit of a plateau. This mimics a lot what the global temperatures look like. Kind of a similar pattern. If you go back and forth between the two. The west is sort of mimic what the globe has done. I'll skip this one. This is what precipitation has done. There hasn't been a lot of change through time. One interesting thing on this diagram, though, is that you see this variation here up till about the 70s has really accentuated a lot between the highs and the lows and periods of high and low, episodes of high and low over the last 30 years or so. So it seems to have been a change in the variability characteristics in the western states. I think I'll skip that one. I just want to say a little bit. There's been a study that was done of 2-day events over the last 60 years or so, and basically this was done by Cliff Mass and Company at the University of Washington, looking at events that occur on the top 20, which would be once every 3 years. Top 60 is once a year. So the blue ones are the less frequent. They're a little bit hard to interpret, actually, to me. Because the arrows here point, they've gone up and down in different places on the west coast over time. So it's not really a clear change to me. And when they summarize them on this diagram right here, they seem to have gone up along Oregon and Washington and Oregon, but not so much in California. And if you look at stream flow, there's a sort of dividing line here where the extreme stream flows have actually decreased, and they've gone up. They've decreased south of this line and increased north of it. How about Los Angeles? So here in Los Angeles, this is the wettest day each year since 1949. Well, what has it done? Well, you can sort of see for yourself. I sort of smoothed them out here just to see if there's any kind of pattern. Whether it's going up or down, well, let's look at 2 days. 2 days, the wettest 2 days of each winter. This goes from July through June. The wettest 5 days. 5 days, 5 consecutive days. The wettest 10 consecutive days. Wettest 20, and the wettest 30. I don't know. It's not obvious to me that it's going up or down. But, you know, we hear lots of statements about climate will become more extreme. I mean, we really need to poke into these and see if they, A, what's the basis for the statements, and B, is the atmosphere following, is it listening to those? So this just sort of summarizes those. I'll skip that. This is the gauge at Happy Isles in Yosemite National Park. It's right below Vernal Falls. And this is the highest flow each year. The annual peak discharge. Yeah, the peak discharge is the highest flow each year. It's kind of hard for me to see that this has gone. They have a really great record there. It goes back to 1916. They're continuing it. There's a few big peaks up here, but overall, it's a little hard to say that it's getting more extreme. Except this period seems to be more extreme than this period, for whatever reason. But this break here is about 55 or 60, right, somewhere around there, the last 50 years or so. So I was say a little bit about the freezing level, which factors in quite a bit to precipitation and hydrology. The freezing level over Lake Tahoe has actually been climbing. This is about 100 meters here, about 300 to 350 feet. It's gone up, and last year it fell down quite a bit. This is a calendar year. But in general, the freezing level has been going up. So this is a really interesting issue with the hydrology. When the freezing level goes up, the snow level goes up in the mountains. There's a couple more things here I'll finish out. We have a lot of this information available on our website. You can go and get information from all of these sites in something called CalClimb. I just want to point out a few of our gaps in understanding here. We don't really know the ties to the western storms to the global climate. How orographic enhancement, in other words, the effect of mountains on precipitation, we don't know enough about that. The global and regional radiative forcing history, especially from aerosols. We concentrate a lot on greenhouse gases, but not so much on these little particles, which are really, really important for global climate. And they also relate to dust falling on the snow, and also dust can help, these small particles can suppress precipitation. There's some unknowns that we haven't really concentrated on, especially clouds. It's a perpetually difficult problem in climate. I just pointed out aerosols, relationships to the deep ocean. That's ultimately going to affect the land parts of the world. The biology is really complicated, but it plays more of a role in climate than we had originally thought. And we're seeing a lot of the issues with the ice sheets right now, which form really slowly but can disappear in a hurry, because formation is a dry process. Their demise is a wet process, and we seem to be seeing that right now, especially with Greenland. So it's all one giant system. Everything is working together here. Figuring, you can't understand the climate of Los Angeles unless you understand kind of the climate of the whole world. Understand climate anywhere, you have to understand climate everywhere. I think that was the last slide I had. It took a little longer than I was going to.
Okay, thank you, Jerry. So this is what I'll be covering tonight. Going to be looking at a little bit of background on California's water infrastructure and setting. How did we get to where we are today? A little bit more about the infrastructure, kind of putting what you have here in Southern California in context with the rest of the state. And then just a really brief cameo on climate change at the end, because that's going to be kind of the teaser for the fourth lecture in this series. So, California, we're actually fairly insular as western states go. Most of our water resources actually are intrastate waters as opposed to interstate waters. Our only major interstate waters are the Colorado River and the Klamath, and then some small stuff around the Lake Tahoe area. Now, a little bit of background. We are the most populous state in the nation. We're also the #1 ag state in the nation. Been the #1 ag state in the nation for more than 50 years. And guess what? Both people and agriculture need water. So just a little background on the physical setting. Half the population in the state, roughly speaking, lives within the service area of Metropolitan Water District of Southern California, which is where we are right now. Central Valley is the major source of our irrigated agriculture production. A little review of geography. Here is the Central Valley, 80% of our ag production. The other two major ag production areas in the state, down here in the Imperial Valley, and then the Salinas Valley in this area. And of course, most of the population concentrated roughly from here south, more on the coastal side than on the inland side. And as Kelly showed on one of his slides from a PRISM data plot, essentially it's a lot wetter in Northern California than it is in Southern California. These are isohyates, or contours of precipitation in inches per year. Darker is wetter. The North Coast is the wettest part of California. And as Kelly also mentioned, just a few storms one way or another makes a big difference. This is an illustration of our last dry year in California, which was 2009. We plotted the 10 biggest storms as with the arrows, size of the arrows representing the relative amount of precipitation they contributed to a precipitation index that we use to look at wetness in the state. So those are the 10 biggest storms in 2009. Only about half of them were very large. And what that really says is a few storms one way or the other really depends on whether we have a drought or we have a wet year. In terms of numbers, if you want to look at some numbers here, average annual basis, the amount of precip that falls on California on an average year would amount to 71 million acre-feet of water. Add in our interstate water sources, primarily the Colorado and Klamath, brings you up to 78 million acre-feet. And we definitely have an imbalance between where the water is and where the people and where the agricultural needs are. And this imbalance has driven water resources activities in California for a very long time. So what are our largest rivers? The ones on the left side of the screen are largest rivers based on runoff. And you notice they're all in Northern California. We have the two on the north coast, the Klamath and Eel, and then our two workhorse rivers, so to speak, which are the Sacramento and San Joaquin rivers. Those are the rivers, the Sacramento and San Joaquin, are the two rivers that actually supply a very large percentage of the developed use in California, even down here in Southern California in the form of imported water supplies. And I should mention that they're listed on this slide. The biggest ones are first on the list. Now, on the other hand, if you come over and look at it in terms of watershed area, well, we still have the Sacramento and San Joaquin there, but we actually do have an entry now from Southern California. Anybody know where the Amargosa River is? Death Valley. It has a very large watershed, but there's no water in it. Oh well, that was your entry for Southern California. You could actually almost think of it as a fossil river if you want to, because it's actually a relic from the Pleistocene times, geologically speaking, when conditions were very much wetter throughout the western U.S., and we had these great lakes that are now dry lake beds. For example, Mono Lake is a much smaller remnant of what was a much larger lake at one time. And the Amargosa, just like the Mojave River, actually, is a remnant of a time, a geological remnant, if you will, of a time when climatological conditions were much, much wetter. And if you want to know more about that, please do check out our exhibit on the second floor. Sorry I had to do that. That was a plug. Okay, so when we look at the story of water in California, one way to answer the question of, well, how did we get to where we are today in terms of water, is to look at it from a historical perspective and say, what kinds of conditions drove the development of water to where we are today? So we'll just quickly run through some of these. First European settlers to move into California were the Spanish missionaries. We had what some might say is our first water project in the Pueblo. It was then the Pueblo de Los Angeles in 1781 when the Zanja Madre, or Mother Ditch, was constructed to divert water from the Los Angeles River for the Pueblo of Los Angeles. A couple of the missions, very early on, completed some fairly significant waterworks for the time. They didn't have water where they were located. They needed to move water to where they were. So the mission at San Buenaventura constructed a 7-mile aqueduct from the Ventura River, which was completed in about 1815 to water their mission facilities. San Diego mission, a 6-mile aqueduct and a dam on the San Diego River to supply their area. So even these very early establishments in California recognized the need to make the water work for them and move it to where they were, because they weren't where the water was necessarily. At the more or less contemporaneous with the period of the missions and then moving into even the gold rush period, we have the era of these big cattle ranchos. And any of you that had to read Henry Dana's 2 Years Before the Mast, perhaps in school, remember his stories in the 1840s of sailing on the coast of California to collect hides from the hide trade, because these immense ranchos, which covered California, that were Spanish and then Mexican land grants, took up vast amounts of land to raise cattle, first for the hides, and then later after the gold rush and many people arrived who needed meat, later for meat. However, this whole system was based on what we would call completely non-irrigated agriculture. They had no facilities to control water, move it around. They were just 100% dependent on whether it rained or did not. And to illustrate the variability that Kelly was talking about and the climate of the system, the rancho system collapsed very abruptly in the 1860s as a result of weather. First came that very large flood in the winter of 1861-62, when Sacramento was much underwater and Leland Stanford had to row to his gubernatorial inauguration in a boat. Well, that drowned a whole bunch of the cattle on the ranchos. And then what happened? The next couple of years, extreme drought. So the cattle that didn't drown basically starved because there was no pasture for them. And that essentially completely wiped out the rancho industry, if you will, in Southern California and seriously diminished it in the Central Valley, setting the stage for a transition to a different kind of agriculture, one that was not based on livestock raising, but instead based on first wheat production and then other varieties of crops. But this is a really good example of, if you didn't have any ability to control what was happening with your water system, you're completely at the mercy of Mother Nature, and Mother Nature can be extremely variable. So this was really the 1-2 knockout punch, going from extreme flood immediately to extreme drought and taking out this entire cattle industry with it. So the gold rush, a very defining time for California, both politically in terms of California rapidly becoming a state, having a huge increase in population, but also very important for water management, because that actually set the stage for much of the state's water management infrastructure and development as we know it today. And it would actually be very hard to imagine what California would be like from a water standpoint absent the gold rush. When the miners surged into California in 1849, they brought a number of changed conditions, if you will. First of all, because they had to get water, do the mining, they had to quickly figure out how to move water around, handle large quantities of water under high pressure for things like hydraulic mining, which is what is this is showing here. They developed some new technologies for what was then very high pressure riveted steel pipe that was unprecedented in terms of the technology of its time. But in order to move the water around in the mother lode where they needed it to do their mining, they constructed a massive system of flumes, ditches, canals, etc., and many of these are still in use today. Some cases, it is still a wooden flume, just like the miners would have built at the time. It may have been rebuilt a few times, but there are actually a number of rural communities in the hinterlands of the Sierra Nevada foothills that are relying on Gold Rush era water infrastructure. And we're reminded of that every few winters when there's a big landslide that wipes out somebody's ditch or flume, or in the summertime when a forest fire comes in and burns their wooden flume. It's amazing how much of this initial infrastructure we have that still remains. But in the area of the Yuba River Canyon alone, which is a very highly productive area of the gold mining industry for hard rock mining and hydraulic mining like this, By 1860, there was more than 1,000 miles of ditch in this one watershed. So these people moved a lot of ground, moved a lot of material, built a lot of infrastructure that laid a foundation for the hydroelectric power industry that I'll talk about in a minute, as well as some of the agriculture that was to follow. They also began the development of a legal system for managing water called the doctrine of prior appropriation, and that actually spread east from California to encompass how we manage water throughout the West. The miners came, they needed water, they took water, they put it to use. And in the mining camps, there became this rule that was established that if you were there first, you got the water. And this was very much in contrast to the system of water management that came to much of the eastern part of the U.S. through English common law, which was called riparianism, or riparian water rights, meaning that people who lived or had property next to a waterway were allowed to divert water from that waterway into their property. And in a time of shortage, everyone shared that shortage equally. Everyone owned an equal access to the water, if you want to think of it that way. Under the prior appropriation doctrine, it is first in time, first in right. And that is the concept that has really been enshrined in Western water law, courtesy of the activities that began in the gold fields. And also because of this kind of mining going on here, this hydraulic mining, they created a lot of flood control problems that we still deal with the consequences of in the Central Valley today. And we'll be talking about that in lecture number 3 of this series when we talk about floods in California. So we owe a lot to the initial activities of the miners when we think about how water in California developed. So something that most people don't realize is that the hydroelectric power industry hugely owes much of its roots to the world of the miners. First of all, if by the time of the 1880s, when Thomas Edison invents the electric light bulb, most of the easy gold has been removed from California. All those individuals out there with their pick and shovel and their burrow, their day is gone. We're talking about large commercial operations, largely, that need to do a lot of heavy lifting, move a lot of material, and it would be really helpful if they could use this newfangled thing called electricity to do it. Well, an individual named Pelton, and the story goes that he got this idea from watching a Ferris wheel at the World's Fair, developed the idea for something called the Pelton wheel, which is basically a type of turbine, which is hugely more efficient than just, say, your old-style water wheel that you have in a grist mill. And this quickly became the technology that was put to use to develop electrical energy, which was first used in the mines to power heavy machinery and do lighting, but then very rapidly spread to do other things like light people's houses. And this was a hugely innovative time in terms of technology. It was really the equivalent of the dot-com era at this time, and they went very quickly from like the Commodore 6400 or the Atari or something like that, the little bitty box that you used to have in your desk that had these 2 giant floppy drives in it. They went very rapidly from that, to let's say an Apple iPad or something like that. In terms of technology, you had hundreds of very small power companies that were established to develop hydroelectric power, usually by buying out rights to a ditch that the miners had first dug. These power companies moved in, acquired these ditch rights, built up these little empires, and they were swallowed up by the next biggest company. And you had this whole proliferation of small privately owned electric companies that coalesced to form in Northern California, Pacific Gas and Electric Company, and Southern California Edison. And although their initial roots were pretty much 100% in generating electricity through hydropower, obviously they have later moved on to other technologies, thermal technologies, including nuclear power plants. So this was where the hydroelectric utility industry really got its start in California. And I have to point out that how many of you think that Lake Tahoe, if you ever heard of Lake Tahoe, how many of you think it's a natural lake? Or it's an untouched lake, I should say. No takers on that one. How many people know there's a dam on Lake Tahoe? It's amazing how many people don't know there's a dam on Lake Tahoe. As part of this effort to develop power sources in the Sierra Nevada, first dam on Lake Tahoe was actually probably constructed to be able to control water from moving logs, but very shortly thereafterwards, dam was constructed for the purpose of electrical generation. This is the existing dam on Lake Tahoe today. It's been stiffed up a little bit since the first version was built, but this dam controls the upper 6 feet of Lake Tahoe. And the storage that it controls by doing so is almost 800,000 acre-feet of water. That's the same size as Diamond Valley Lake, which is the largest reservoir in Southern California. So this little bitty 6-foot dam, actually it's about a 10-foot dam, which controls 6 feet of the lake. And I'm going to show a slide later on with a picture of Diamond Valley Lake, which has an immense dam in comparison and only develops the same amount of water, roughly the same amount of water. So it's that old adage about location is everything. So, of course, when the 49ers arrived here in California, they needed to eat. And also some of them realized that, this gold mining business was really hard work. And it entailed, standing all day in freezing cold water shoveling dirt. Maybe it was more fun to be driving a team of horses behind a plow or something like that. But people quickly realized the agricultural opportunities in California and rapidly moved into the world of irrigation. And just as in the electrical power industry, there was this huge inrush of capital to develop these small private power companies that eventually grew into larger and larger power companies and consolidated. There was an initial effort to develop irrigation through private irrigation companies, because people realized pretty soon, we had this drought in the 1860s, major drought, which made it pretty much very apparent to people that the only way they were going to be able to farm profitably in California was through irrigation, because, as we know, it doesn't rain in California in the summertime, which does make it kind of hard to grow crops if we don't have water for them. So they're thinking about how to go about doing this, and along the way, we have this court decision here. I mentioned that the prior appropriation doctrine was something we got from the mining era in terms of the ability to claim a right to water. Well, California is the only one of the western states that also recognizes riparian rights. So we have a dual system of water rights, and this basically came out of this piece of litigation, which actually was instigated by some parties of some individuals who were involved in buying out the remnants of some of these Mexican cattle ranchos that I mentioned. And a couple of them, who were actually sort of business partners, got into a major dispute about whose right was more important, the right of the riparian landowner or the right of the appropriator. And the court sort of gave them a very middle-of-the-road decision by saying, well, you're both right. You both have claims to right, which is why California recognizes both of these kinds of water rights. But because there was a lot of activity going on in these early decades after the gold rush, figuring out how to structure agriculture in California with respect to the water issue. And as this debate was going on about private irrigation companies, should it be public agencies, those kinds of things, in response to this, the legislature did something important in 1887. They passed a statute that enabled the formation of irrigation districts, a type of special district whose job it was to control and manage water and sell the water to people that lived within the district. And also, this debate is continuing between private sector, public sector formulation of irrigation districts. And as this goes on, ultimately the federal government passes the Reclamation Act in 1902, which applies to the 17 western states west of the Mississippi. And the big reason for this getting through Congress, and it was a fairly contentious debate, was the recognition that in states like California, the ability of the private sector to have the resources, the capital, the ability to put together and operate an irrigation district was simply not within their financial capabilities, something that was really emphasized in a number of places, particularly in the San Joaquin Valley in California, where you had a number of what were called private irrigation colonies, even, that essentially went bankrupt because they started a project, and after a couple of years of running it, they ran out all their cash, and they simply did not have the money to build the kind of infrastructure that was needed. And the need for a very deep pockets entity was really emphasized in southeastern California in 1911 when the California Development Company went bankrupt because of the Salton Sea. They were a private irrigation company in Imperial Valley that had some control works on the Colorado River. A big flood came down the Colorado River. Most of you know the Salton Sea was created by a flooding on the Colorado River that breached the irrigation headgate system and flowed unabated into the Salton Sea for a long time until the federal government and the railroad basically got together and stopped that flow. But that was an illustration of how limited the resources of private entities were in terms of being able to afford the kind of big water infrastructure that was associated with developing the West. And California has the distinction of having two of the earliest reclamation projects in the U.S. The first, in fact, was called the Newlands Project, after Senator Francis Newlands, who was the author of the legislation. And that dam at Lake Tahoe that I just showed you, that was a facility of the Newlands Project. Bureau of Reclamation, under an easement from the private power company, took over that dam to develop the water of Lake Tahoe for irrigation in Nevada. And probably the second or third oldest reclamation project in the U.S., depending on whose statistics you look at, is the one that's pictured here. This is Upper Klamath Lake in Oregon. This is the Klamath Project up at the extreme northern border of California with Oregon. And of course, the biggest irrigation project in California is the Federal Central Valley Project. It was originally planned by the state of California as it was going to be a state irrigation project. California attempted to sell the bonds during the Great Depression and at that time could not manage a bond sale. So the federal government stepped in and took over the project, and this was at a time when there was the initiative to put people to work through the WPA, the Works Project Administration, and other programs like that to deal with the impacts of the depression on the economy. So a lot of people were put to work in building the CDP, and its Keystone facility, Shasta Dam, was actually completed in 1945. So what about the urban development that was going on along with this agricultural development? City of Los Angeles was the first large municipality to reach well outside its borders to find more water to bring into its service area. And in 1913, when the city completed the first barrel of its aqueduct up through Owens Valley, the population of the city of Los Angeles, relatively speaking, was not all that large compared to, let's say, San Francisco or other communities at the time. However, Los Angeles had been settled in an area that was frankly pretty water supply deficient. So that forced them, even early in their development, to go well outside their boundaries to look for a water supply. A couple of decades later, you have the communities around the San Francisco Bay Area, the East Bay, Oakland area, and then the city of San Francisco, going to the Sierras to find water because they've outgrown their local supplies. And in 1941, Southern California, again, goes outside its boundaries for water and goes all the way to the Colorado River. Metropolitan Water District was essentially initially organized through the efforts of some of the communities outside of the city of Los Angeles who weren't participants in the original Owens River aqueduct, but still needed water of their own to grow. Pasadena, for example, was one of the early members of the Metropolitan Water District. Now, something that was very apparent in the California political thought process is as World War II was going on and drawing to a close, it was very apparent that California's population was absolutely just mushrooming. And in fact, the legislature held a whole series of hearings in, say, 41, 42, 43 timeframe, talking about, well, what are we going to do when the war ends and all these people are going to want to live in California? Because they recognized, particularly in Southern California, there was going to be a huge buildup of population. Uh, the defense industry is people coming back, people who had been through California because they were in the service in the wartime, coming back to settle there. And that started a pretty massive planning program for infrastructure, both water infrastructure and highway infrastructure. But in the 1950s, a series of comprehensive water plans were put together for what would a full development of the state's water resources look like, what projects would this mean. And out of that planning process came this idea of a state water project, actually the second time that California tried to build a state water project, and this time we didn't have a Great Depression, so the state went ahead and built the State Water Project, which is primarily an urban water supply project, takes water from Northern California, delivers it both a little bit around the Bay Area, some of the San Joaquin Valley, most of it down here. And also interesting to point out that California in 1962 became the nation's most populous state. In 1900, California was ranked 21. So 1962, most populous state, and it seems like we've been the most populous state forever, doesn't it? So that's been a long time. So anyway, through this process of various needs coming together, we've built up this extensive system of water infrastructure that Kelly had alluded to, in which we move water all over the state. So for example, the State Water Project, which I just mentioned, we have Lake Oroville up here. We have aqueducts that serve water to the North Bay and the South Bay. Major California California aqueduct running the length of the San Joaquin Valley over the Tehachapi's, coming down here into Southern California. We have the facilities of the Central Valley Project, again, primarily an agricultural project here within the Central Valley. And then we have the water systems that bring, local systems that bring water to Southern California, including Metropolitan Water District, Aqueduct, and the City of Los Angeles. But not to forget that groundwater is also an important source of supply in California, and about 30% on average, rough average, long term, maybe up to 40% in drought years, because when people's surface supplies are cut off, they will turn to groundwater. We have lots of groundwater basins in the state, shown here in blue on this map. However, many of the basins don't have much water. If you are over here in the desert area, we show lots of little groundwater basins out here. Technically, they're geologic formations that can hold water, and some of them may have a little bit of water in them. But since, as Kelly pointed out, it doesn't rain very much over here, they're not getting a lot of recharge, they don't hold much water. Central Valley is the major groundwater resource in California. Down here in Southern California, South Coastal Plain, where we are, there are some fairly decent-sized groundwater basins here. Many of the ones in Southern California have actually gone through a court adjudication process to allocate rights to this water. One of the issues that was recognized very early on in California, about by 1950 or 1960, almost every coastal groundwater basin in the state that had any level of population development on it was having problems with saltwater intrusion. And that spurred a lot of activity to decide how to manage these basins. And here in the most intensely urbanized part of the state down here, that resulted in court adjudications of many of the basins. Interestingly enough, up here in the San Francisco Bay Area, there hasn't been that kind of activity because the groundwater resources are so minimal, just because of the way the geology works, that has been less of an issue. So talk now just very briefly about the characteristics of some of the projects to give you a better feel for how what you have in Southern California compares with other facilities in the state. So largest water project in the state is the Federal Central Valley Project, which is a conglomeration, if you will, of a number of different facilities. The combined storage capacity of all the CVP facilities is about 12 million acre feet. So keep that number in mind. And interestingly enough, it's also the largest generator of electrical power in California. We look at the State Water Project. It's the second largest water project in California. It's operated by my agency, the Department of Water Resources. We're actually the largest consumer of electrical power in California. And that's because we lift water 1,900 feet up over the Tehachapi Mountains to bring it down to Southern California. We do generate some power, but we're only the fourth largest generator in the state, and obviously a lot of different kinds of facilities. We look at local water projects. They come in various sizes, shapes. Here I've shown a picture of one that is a groundwater storage project. This is one of the larger groundwater recharge facilities of Los Angeles County, the Rio Hondo spreading basins. Not terribly far from here. Wide variety of local water projects out there. We always get asked the question of, well, what about water recycling and desalination? How do they compare in size to some of these other projects that we look at? So let me first start with talking about the groundwater ones to put it into perspective. So I mentioned Central Valley Project, our largest water project in California, with a storage of 12 million acre feet of developed storage capacity. Well, if you look at the largest of the groundwater storage projects in California, projects that are designed, managed, intended to store water in a groundwater basin, kind of analogous to the way you would operate a reservoir system. In California, we have about a dozen of what I would call large groundwater storage projects. Several of them are over 1 million acre feet in size. All of them are located either in the San Joaquin Valley or in Southern California. And that's because to have a groundwater storage project, first you have to have a place to put the water. That basically means you need to have a relatively empty aquifer, a groundwater basin. And the reason that you have a relatively empty aquifer, a groundwater basin, is because there's already been enough use of groundwater or development of groundwater to have emptied it out. So that means you're going to have a basin, an empty basin in an area where there's high water demand. San Joaquin Valley is agriculture, in here is for urban demand. You need to have the facilities to move water in and out of the basin, and you need to have a source of water to put it in and out. Here in Southern California, as in this basin here, they're basically recharging wet weather water, or flood flows, if you will. There's not a lot of surface reservoirs in Southern California, as you've noticed. A lot of the local supply does come from groundwater, and to the extent that agencies like Los Angeles County or Orange County Water District are able to manage these flows and put them into groundwater storage, this is how you make water available here. Now, how does this compare with the much smaller local projects like water recycling and desalination projects? Well, you can look at planning reports for California back in the 1950s and 1960s, in which these reports very confidently say that, well, within the next couple of decades, California will be getting all of its water from the ocean. Well, there are some obstacles to that, like cost and etc. But to put this into perspective, some of you have probably seen some news articles about some large desalination projects that are in planning, or more accurately have been in the litigation and permitting phase for some time in San Diego County, for example. There's a public-private partnership. The private company is called Poseidon Enterprises that has been working for some years to attempt to build a plant at Carlsbad. And the plant would be what would be called a 50 million gallon, or MGD, sized plant. That's worth about 55,000 acre feet a year if it were to become operational. Currently, there are only 2 desal plants of that size operating in the U.S. today. One of them is in Tampa Bay, Florida, and it treats estuarine water. It's a little less salty than seawater, therefore cheaper to treat. And then a brackish groundwater plant in El Paso, Texas, that's even cheaper to operate because it's dealing with water of lower salinity. So, biggest projects in the U.S. now in the 55,000 acre foot range in comparison to some of these surface water and groundwater storage projects that are much, much larger. And if we look at what you have locally here in Southern California, biggest reservoir in Southern California is Metropolitan Water District's Diamond Valley Lake, which was built, roughly 15 years ago or so, 800,000 acre foot storage capacity, or to put it another way, just a little bit larger than the top 6 feet of Lake Tahoe, which are controlled by that small dam. A couple of the local groundwater recharge projects in Southern California, the larger local groundwater recharge projects, maybe on the order of 300,000 acre feet or so, more or less annually, something in that ballpark. So quite a difference between that and what a desal plant might provide. And in fact, there's only a handful of desal plants, seawater desal plants, that have been operating for any length of time in California. There's one up by Monterey, for example, at Marina Coast Water District. Its output is in the range of a couple thousand acre-feet a year, something like that. So major difference in size among these different kinds of facilities. So where specifically does Southern California's water come from? If it doesn't come from all these little local sources, here's a breakdown on the numbers. Long-time historical average, about 60% imported water supply from these three sources. The Colorado River making up about half of that. And local sources, which is primarily groundwater, augmented by water recycling projects, very little bit of desal, amounts to about 40%. One of the things that we see as a goal for the future for Southern California, though, is the need for Southern California to develop more of its local resources, because these imported sources all have challenges with them. Colorado River, now the lower basin of the Colorado River, is at its full allocation that's permitted to it under the Interstate Compact. In the long term, we're concerned about the impacts of climate change in the basin. State Water Project, we have the challenge of being able to divert water to Southern California because of the issues associated with the San Francisco Bay, Sacramento, San Joaquin River Delta, or Bay Delta, most formally, and Los Angeles aqueducts. The yield from these aqueducts has been reduced substantially in the last 20 years due to the need for Los Angeles to meet air quality requirements in Owens Lake, which means they have to divert water from there, or not exercise all the water they could develop to meet that, and also the environmental requirements for the tributaries around Mono Lake. So essentially the reliability of these imported supplies is probably going to be less in the future, and we are worried about the impacts of climate change on these water sources that come from the Sierra Nevada, because we do expect there to be impacts in the long run from climate change there. So can't talk about California water without saying just a couple of words about the Bay Delta. It is where we move a lot of our water around through this great system of infrastructure that we have. It's an ecosystem that's been highly altered since the days of the gold rush, when it was first a series of tidal marshes that were later diked off and leveed up and converted to farmland. And it is certainly a great challenge in terms of infrastructure and resource management. It is a very different system than what it looked like back in 1849. We have a vast network of constructed levees, many of which were constructed by mules and scrapers, certainly not to modern engineering standards, and we know that many of them have had their failures. California's first state engineer, back right around 1900, had a famous quote about we only have two kinds of levees, those that have failed and those that are going to. And he was probably thinking about some of these levees when he said that. And there are a lot of challenges with respect to the ecosystem. The fact that the ecosystem that we have there today has an awful lot of contributions from places as far away as Japan. One of our most successful species in the estuary today is the Asian clam, which just seems to love the place and probably is affecting what's left of the native species by virtue of its impacts on the food chain. So, what are some of the challenges that we face from a water supply standpoint looking forward? Well, I mentioned there was going to be a very brief climate change cameo at the end, and this is essentially it. This is the one slide. We say that, well, we're going to have reduced snowpack in the Sierra Nevada. Not good, because this snowpack acts as a major reservoir for our water management systems. And by the way, none of our facilities were designed to handle a huge slug of floodwater much earlier in the season, because we operate our Sierra Nevada reservoirs to balance operation between storing water for future use and releasing water to provide flood protection. There are certainly going to be ecosystem impacts to salmon, which are one of the fish that hugely influence water management in Northern California. There are cold water species they're not going to be happy with warmer water temperatures, which probably means there will be some impacts on water projects related to that. Sea level rise is not going to be good news for San Francisco Bay or the Delta. It has both flooding issues for levees and also increasing salinity, which brings issues for the ecosystem as well. And then with warmer temperatures, typically you expect to see higher water demands for either your urban landscaping or your crops. So, 2100 maybe not looking like necessarily the best time from the standpoint of climate change. So this is where I wrap up and ask if there are any questions, or how Jerry wants to handle questions.
Jeanine, thank you very much.